Hello there, great person, and welcome to my weekly science reaction. Today we're gonna react to a video called String Theory Explained. What is the true nature of reality? So yeah, let's get into string theory. I know some things quite exactly, some things I have no clue about. Yeah, for those of you who are new here, I'm a quantum physicist, at least in part psychologist, but yeah, so it's something I know a bit about, and I will tell you my thoughts on whatever they will present us today. And Kurz gesagt is quite a good channel. They have great visuals, great things yeah, the way they explain, I really like it, and let's just watch it. And yeah, so be warned, I will pause the video, so otherwise I will lose my thoughts in the end, and I have a lot to say sometimes, and I just can't hold it in. Sorry. I mean, it's not that bad, but yeah. So let's just get into this. So mouse went away. So let's go. What do we have today? Kurz gesagt. Universe stuff.
What is the true nature of the universe? To answer this question, humans come up with stories to describe the world. We test our stories and learn what to keep and what to throw away.
Yeah, okay. Already there. That's quite true. That's what I would have said as well, because I know a lot of people that belittle other people that, like, how do I say this, believe in older stories. And the old stories are what brought us where we are, so you should never, say, they don't matter anymore. We have science that's, why would we need it? Like there's this sometimes this, yeah, we are rational people, beliefs, they don't matter, we can just use science. No, you can't. I don't think you can. I know there are people who claim that they can, and yeah, I rarely disagree with those. But so yeah, stories are quite important. It's like he said here, stories, and you test them, and then the stories get more precise because there are things about the stories that you can keep and things you have to throw away because some things don't work out in reality, some do, and then you take stories, and if you do that for, I don't know, 3,000 years, you end up with science. You know, it's like that. Science is a very condensed story, and as well, what I find quite interesting is that, you have this cognitively, you have this layer that's very very primal, this, like, you take your instincts, your instincts, and they rule you, and then above that you have these things like this part of your brain where you think about pictures, and that's the part where suddenly stories start to emerge, and then you take the stories, and then you have another brain part that's on top of that, so grown from that, which is used for science and stuff, and processive, I don't know the word, but to think in algorithms, so to speak. I mean, in rational algorithms. So yeah, I mean, we are rooted in religion and stories and myth and legends, and so that's, yeah, and he's quite right, and it's exactly that what we do in science. We test the stories in the world and we throw them away when they do not, give the results that are observable. So yeah.
But the more we learn, the more complicated and weird our stories become.
Oh, I hate
Some
the
of them
zeta function.
So much so that it's really hard to know what they're actually about. Like string theory, a famous, controversial, and often misunderstood story about the nature of everything. Why did we come up with it, and is it correct, or just an idea we should chuck out?
Yeah, so string theory, as far as I know, and that's what I know, it's a mathematical theory. It's not a theory from physics. It's a mathematical building, so to speak, that works exceptionally well, and if you tune it in the right way, you can obtain our universe. But you can also put in other things, and you would have universes with different laws of physics. So it's just like, yeah, let's try to, like, have the math first, and then we see whether the world fits. it's like a bit like quantum physics. It was the same there, at least in part. So yeah. So we've got a Bohr atom here. Oh no, it's rather Ford, I think. So yeah. Let's see what they do with that. Molecules. Oh, it's their intro. Yeah, I'm an idiot.
To understand the true nature of reality, we looked at things up close and were amazed. Wondrous landscapes in the dust, zoos of bizarre creatures, complex protein robots.
I like tardigrades.
All of them made from structures of molecules made up of countless, even smaller things, atoms. We thought they were the final layer of reality until we smashed them together really hard and discovered things that can't be divided anymore. Elementary particles.
Yeah.
But now we had a problem. They're so small that we could no longer look at them.
Atoms as well, though. That's something often misunderstood as well. These pictures of atoms you see, and I've said it before, these like balls where things fly around, that's absolutely, you know, that's the physicist's perspective from 98 years ago. You know, it's so old. So it's like we've been there. That's over. Long time over. And you can't see atoms. You can shoot things at atoms, and by them bouncing back, you can, so to speak, get the shape of atoms on a photograph, so to speak. But it's not really the atom that you see. Can't see atoms. It's physically impossible. You can also not see elementary particles. That's also physically impossible.
Think about it. What is seeing?
Yeah.
To see something, we need light, an electromagnetic wave. This wave hits the surface of the thing and gets reflected back from it into your eye. The wave carries information from the object that your brain uses to create an image.
That's also not how a photon looks like, by the
something
way.
Without somehow interacting with it. Seeing is touching, an active process, not a passive one.
Yeah.
This is not a problem with most things. But particles are very, very, very small. So small that the electromagnetic waves we use to see are too big to touch them. Visible light just passes over them. We can try to solve this by creating electromagnetic waves with more and much smaller wavelengths. But in quantum physics, shorter wavelengths means more energy. So when we touch a particle with a wave that has a
I don't think it's only quantum physics. I mean, yeah, it's E equals HF or H nu, but that's not completely quantum physics yet. It's also a bit of older physics even.
A lot of energy, it gets a kick. By looking at a particle, we change it. In quantum physics, we cannot know where a particle is and where it's going with absolute precision. This fact is so important that it has a name, the Heisenberg uncertainty principle, the basis of all quantum physics. So what does a particle look like then?
I would not say that that's the
nature?
basis.
We don't know. If we look really hard, we can see a blurry sphere of influence, but not the particles themselves. We just know they exist.
Ooh, dangerous territory. We're entering dangerous territory now. He was right, of course, but that's purely metaphorically what he said. You know, this fuzzy cloud he spoke about, it's purely metaphorical. There is no cloud. I mean, no, there is no cloud. It's like a story let's do it like that. It's the story you can tell. You know, you can say, yeah, there is a cloud. Imagine there's a cloud, and there are things in the cloud. You say something like that. Yes, it works to a certain extent, but it's nothing. It doesn't make sense to say that's how it looks. Doesn't make sense.
But if that's the case, how can we do any science with them? We did what humans do and invented a new story, a mathematical fiction. The story of the point particle. We decided that we would pretend that a particle is a point in space. Any electron is a point with a certain electric charge and a certain mass, all indistinguishable from each other. This way, physicists could define them and calculate all of their interactions. This can be made precise in quantum field theory, and this solved a lot of problems.
I don't know how I think about that. That's very difficult to think about. He is right that you take space-time and you interpret it as being distinct points, perhaps, something like that. And then you can say, yeah, and on one of those points I can measure it. But the point itself is fuzzy as well because of the Heisenberg uncertainty principle, he said it. So you can't really have that point. You can't really determine the point. And if you would try to determine the point, that doesn't make sense. Makes absolutely no sense. So, and yeah, I don't think this is correct what you said. I don't think it's correct in a way that it's something useful to think about. You shouldn't think about it like this, I think. You should think about this as a particle is an entity of something, but not a spatial entity, not purely. That's the problem. You might, yeah, you run into a lot of problems when you think that particles are like points in space that move through space. And yeah, there are things like you can. I mean, he's right. He's right in the way that he says, yeah, it's a story. And that's how you have to look at it. That's how you have to look at everything he says here. It's a story. It's not the reality. It's not reality because you can't tell. Reality, I mean, that's the crazy thing about quantum physics, that it tells you that the reality you are used to in the 3D world is not the reality that we can describe with the theory. So yeah, it's a story. So yeah, so let's do that. Let's say, yeah, we imagine like little balls somewhere that are lying around, and now we look at them, what they could do and what we could do with them. So yeah, I mean, it's also, I really like that he does it this way. This is a very good visualization because obviously the quarks don't look like this. It's like the shapes mean that they are different. That's all they mean. And it's the same idea Plato used 2,500 years ago. Same idea. Or Archimedes. I think Archimedes thought about it a bit as well. Aristotle thought about this, and the idea that that rudimentary portions of anything are like different shapes. That's one of the oldest ideas ever in science. Perhaps the oldest idea in science, one of the oldest ones. And yeah, so yeah, let's imagine this. Let's imagine we are looking at this. And I will shut up.
All of the standard model of particle physics is built on it, and it predicts lots of things very well.
Yeah.
Some quantum properties of the electron, for example, have been tested and are accurate up to 0.0000000000002%.
Yep.
So while particles are not really points, by treating them as if they were, we get a pretty good picture of the universe.
Yeah.
Not only did this idea advance science, it also led to a lot of real-world technology we use every day.
And the phone, by the way, the smartphone.
Gravity. In quantum mechanics, all physical forces are carried by certain particles. But according to Einstein's general relativity, gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage.
Yeah, that's a very good story.
Gravity is a theory of geometry, the geometry of space-time itself, of distances which we need to describe with absolute precision. But since there is no way to precisely measure things in the quantum world, our story of gravity doesn't work with our story of quantum physics. When physicists tried to add gravity to the story by inventing a new particle, their mathematics broke down.
Yeah, so this graviton thing, we haven't found it. I don't think it exists. Oh, that's purely opinion, really purely opinion. It's something they always predict, and then they predicted at higher energy and higher energy and higher energy. Something that would come closest the Higgs particle, but gravity itself, the graviton with spin 2, I mean, it's theoretically possible to have that spin. In fact, many things have that spin, but Yeah, the last real talk I heard about this was in 2018, back in 2018, and it was a certain scientist, and he presented the newest results of the collider, and he showed us a graph where they had their measurements for a certain range of energies, and he said, yeah, this is our prediction. He showed us a graph, and then he said, and this is what we measured, and it was exactly the same. And what he said here, like this 0.000, you know, percent error, yeah, that was there, but you couldn't really tell the difference between those two graphs. And if other theories that were proposed, like string theory, I think, I'm not sure, would have been the way it is, there would have been other particles already predicted there, and they have not found anything. All they had done was use their particle collider, say for the Higgs particle, to this confirm quantum theory. That was so interesting, and he was. I really realized that it was a bit hard for him to say it like that. But he spun it, and I would have done the same, because it is true what he said. He said it really, really shows that quantum theory is such a good theory. It fits so well. Unfortunately, it fits too well in that domain, so no graviton yet. But let's see what he's telling us about now.
And this is a big problem. If we could marry gravity to quantum physics and the Standard Model, we would have the theory of everything. So, very smart people came up with a new story. They asked, what is more complex than a point? A line or a string? String theory was born.
What? I mean, he's telling us a story. Let's put it that way. As far as I know, it was like they added more and more spatial dimensions because they ran into problems each time. So we have 4 dimensions in quantum physics, 4 spatial dimensions. 1 dimension is time, but that was not enough. So I think they had to add 2 other dimensions to space, and then it was the first version of string theory, and then ran into a lot of problems. Then they had to add 2 other dimensions, so they had 8, and now I think they're at 12. It's a bit, yeah. If it works, it will be the theory. It's not about, is it the theory? It is about, does it work for everything? If it does, it's a theory we use, and down the line we will have another one.
What makes string theory so elegant is that it describes many different elementary particles as different modes of vibration of the string. Just like a violin string vibrating differently can give you a lot of different notes, a string can give you different particles. Most importantly, this includes gravity. String theory promised to unify all fundamental forces of the universe.
Yeah.
This caused enormous excitement and hype. String theory quickly graduated to a possible theory of everything.
That is dangerous. That is very dangerous. There is something very dangerous I see in the research of string theory, and it has nothing to do with the research. It's about the politics of science, and we have gone down the alley of string theory very, very far. And if it should prove to be useless for physics, that would mean that a lot of people's jobs were useless. No, they were not. I mean, they were not useless. Don't get me wrong. This is just me being a bit like what doubters would say. And it's not right, because what they did was exceptional in mathematics, and they achieved so much with string theory. It's a very great thing they did, but it's not physics, it's mathematics. Currently, we found the universe in the string theory because we set several constant parameters in a certain way, and then you can get our universe's laws. But it is a problem that many jobs are solely focused on that, and you have a community that is probably a very great community, and they're working on this, and imagine there would be someone who would show, no, it's not like that. So that's something, yeah, because there's a lot of money that went into this as well. I mean, if you take a paper, it's $10,000 for a paper at least, for reviewing, writing, the scientists you have, perhaps 10 to 15,000 euros, something like that. Perhaps some are less, some are more. So there are so many papers on string theory which try to link it to physics and try to show that it is physics. So imagine what money is in there. And we will see. We will just see if it works. But even if it would not work, I hope that they will have the character to admit it. Because that will be hard. That will be hard. It's like with Einstein, who is often said to have opposed quantum theory and entanglement. And he said it's rubbish, you know? And he had this long discussion with Heisenberg and Bohr. They wrote letters to each other, and Werner Braun, I think Max Born, I don't know, several scientists, and they all wrote letters and they discussed it. And imagine if quantum physics had been wrong, or Heisenberg, all of them would have had their reputation damaged in the community, probably. And it doesn't have to be that way, don't get me wrong, but it's like human nature. It's like human nature. That is something we have to be very careful about. Yeah. But it might be the theory of everything. It might be the theory. We don't know. We have no proof, and we have no counterproof.
Unfortunately, string theory comes with a lot of strings attached.
I love the duck, by the way.
Involving a consistent string theory does not work in our universe with its 3 spatial and 1 temporal dimensions. String theory requires 10 dimensions to work out.
I think
so
12.
String theorists did calculations in model universes, and then try to get rid of the 6 additional dimensions and describe our own universe. But so far, nobody has succeeded, and no prediction of string theory has been proven in an experiment.
Yep.
So string theory did not reveal the nature of our universe. One could argue that in this case, string theory really isn't useful.
It's useful for maths.
Science is all about experiments.
It's very useful for maths.
If we can't do
there
those,
have been
why should we bother
great
with strings?
Theorems
It
created.
really is all about how we use it. Physics is based on maths.
Yeah.
2 + 2 makes 4. This is true no matter how you feel about it. And the maths in string theory does work out.
Yeah.
That's why string theory is still useful. Imagine that you want to build a cruise ship, but you only have blueprints for a small rowing boat. There are plenty of differences: the engine, the materials, the scale. But both things are fundamentally the same: things that float. So by studying the rowing boat blueprints, you might still learn something about how to build a cruise ship eventually. With string theory, we can try to answer some questions about quantum gravity that have been puzzling physicists for decades, such as how black holes work or the information paradox. String theory may point us in the right direction. When used in this spirit, string theory becomes a precious tool for theoretical physicists and help them discover new aspects of the quantum world and some beautiful mathematics.
Yeah.
So maybe the story of string theory is not the theory of everything. But just like the story of the point particle, it may be an extremely useful story. We don't yet know what the true nature of reality is, but we'll keep coming up with stories to try and find out until one day, hopefully, we do know. This video was supported by the Swiss National...
Yeah. Okay. So that was the video. Yeah, I rambled on too long again. Hope you were not that bored this time. Yeah, I like string theory, though I don't think it is... I don't know. I don't know what to think about it. It's such a peculiar case. It's like, we had this once before, as I said. We had this with quantum physics. It's like, there's this formula, we don't know what it means, and then Max Born discovered that if you square the wave function, its absolute value at least, you get probability distributions, and that linked it to reality. And we worked out the whole math of quantum physics, and then we saw it in experiments. Mainly, it's not that easy, of course, but I'm breaking it down a bit. So yeah, it's quite interesting. There's also loop quantum gravity. It's like it's similar, and what I find interesting that what I do my topological research sometimes it's also about these like strips, not strings, strips. So these the idea of a strip is something very powerful in topology, in quantum topology, and I mean it's in string theory, it's in loop quantum gravity as well. So that's the interesting thing. I think all of the recent candidates for a grand unified theory have these like circular things that are somewhere, and either it's the right thought or it's the wrong thought. So either we have to make it more precise what they all do, or we have to completely say, no, we take something completely different, like boarded. Boarded say, yeah, it's not like a circular orbit, it's like a guitar string. It's genius. I mean, it's completely out of left field, but that's why he was such a genius. And Niels Bohr, by the way, loved stories as well, and he saw his model as stories. So the Bohr atomic model, the one where there are distinct orbits and electrons can jump, you know, that was his story. And he said it like that. He said, this is poetry. I understand it not as a depiction of reality, but as poetry of reality. That's what he said about his models. And that's what he said about all his quantum physical descriptions and models. It's like poetry. So that's why I really like that the video here put the emphasis on stories, because that's what physics is. It's what everything is. Everything is a story. I mean, that's the story is the oldest device to transport verbal information. And even before that, pictorial information. So quite good. So I like this video a lot. The problem with visualizations is they always are stories as well. And he said it, I know he said it, I said at a point, no, it's not like this. Yeah, he said it. That was my mistake, but you have to be so careful with the pictures. You have to pay every single picture in physics you have to take as a story. If you do that, you might learn physics. And that it's not supposed to sound condescending or stuff like that. It's like more like an advice. It's what really made me learn physics in the end, because I was not good at learning physics for a long time. And yeah, I've learned learning through several ways, and that helped me a lot, and perhaps it will help you a lot. So if you want to learn science, physics, yeah, take everything you see in these kinds of videos or other videos or in papers as stories that are trying to teach you how things work. And perhaps someone has another story that tells you how something works better. Anyway, I hope you liked this. If you did, consider liking, subscribing. Yeah, I hope you have a very, very great evening, day, or whatever. And perhaps we'll see each other next Wednesday for the next science reaction. And see you soon. Bye.